Okay, so before we jump in on that, we'll just take our quick look at our calendar. Today is October 5th. We are continuing our work in section 2.2, more about functions and their graphs. Today we cover a concept known as piecewise defined functions. We'll define that very soon. Next class, I will hand out project 2. Any questions on the calendar? Okay, so coming back here in our preview exercises, we're going to find the equation of that green line. I've already written the answer here. That's y equals negative 0.4x plus 20. So how do we get that? Well, let's give it a try. First thing we're going to do is write down our basic y equals mx plus b formula. And we're going to find the m, and then we're going to find the b. So to find the m, we need to have 2 points. So 30, 8 seems like a pretty good point to use. It's given. And then the other point I'm going to use is way down here. This is 50, 0, right? You could have picked a different point on the line, but I'm going to grab that one. And then we'll do our slope calculation, which we know is a rise over a run, or change in y over change in x. So the rise going from the 8 to the 0 is, I'm going to call that negative 8 because we actually fell 8 divided by, and then the run from 30 to 50 is 20. So that right there is the slope. And if we reduce that, let's see, 4 goes into both, so that's a negative 2/5. And we'll change that to a decimal, although the fraction is fine too. And so from there, we rewrite our y equals mx plus b, and we say, okay, y is really negative 0.4x plus b, with the b to be determined. And a lot of people forget that there's work involved in finding the b, and they think they should be able to just look at the picture and read the b. And they know that the b has something to do with a y, right? The b is the y-intercept. And so oftentimes I see people grabbing that number and shoving it in for the b because it is a y value. It's not intercepting, right? Said with exactly the right amount of disgust. It's not intercepting the y-axis there. You can't just pick any old y. You got to pick the right y. The right y is someplace way up here, and I can't just eyeball it. I mean, we got to get it perfect, and so we need a process and not just reading off of the graph. And so the process is to say, well, I know that this y equals negative 0.4x plus b is the equation that every single point on that green line satisfies. So for example, if I plug in 30 and 8 for my x and my y, then that point will satisfy this equation. And that's going to be enough for me to find the b. So this becomes, instead of y, what number? 8 for the y equals negative 0.4 instead of x, what number? 30. And then plus the b to be determined. This is the work involved in finding the b. You can't just look at the picture and know the b. You got to do this process. Okay, let's see. So that's, I think that's a minus 1.2. I'm doing something funny here. What am I doing funny? 4, so 12. Minus 12. That's what I was doing. That was funny. So 8 equals negative 12 plus b. And then find the b by adding the 12. So b is 20, right? Add the 12. And then finally, grabbing this equation, I get our final answer here. Y equals negative 0.4x plus 20. Questions on the process? I know this is an old process. It's one that you guys have done many times, but it seemed like some folks could use this brief review. All right, so let's move on to the demo. I guess what I'll point out first with this picture right here, how many rules, how many lines did you come up with? 3, right? 3 distinct equations. There isn't just like one simple equation for that entire picture, yeah? And that's sort of the point for today, is that we're gonna be thinking about new functions where it's not just one simple formula, one single formula, but rather 2 different formulas, or in this case, 3 different formulas. And that's not so uncommon in the real world. Number one, sometimes a function may need more than one formula to accurately model a real life situation. So we're going to read right here real quick a list of things where there's definitely more than one rule that governs the behavior of the thing. So for example, taxi fares. What about taxi fares makes it so there isn't one single formula that tells you how much you're going to pay? Yeah, so mileage, right? There's a mileage fee, right? You know, like I don't know, like $1 for a fifth of a mile or something like that, right? But is that it? Yeah, isn't there also like a stopped in traffic kind of fee, right? If you're in slow traffic, there's that. What else? As soon as you open that taxi car door, isn't there like a fee that, right? And so it's several different fees getting pushed together. It's not just a single formula. US federal tax code. If it were everybody pays 10% of their income, that's what your tax bill is, then there would be a single rule. But it's not, right? Isn't it like a crazy complicated system of rules? Definitely more than one. Typically, how much income you pay is based on what's the main feature that tells you what percentage you pay? Is your salary, right? Your income, right? And so like the people that make the least amount of money, they pay like the smallest percentage. And then as you go up, you start paying more and more of a percentage, right? You're really rich, but paying equivalent. So there's definitely not one single formula for income tax. Same thing, late fee charges for credit cards. The fee that you pay, maybe like if you owe up to $100 on your credit card, then the fee is $5. But if you owe between $100 and $1,000, the fee is this. And if you owe more than $1,000, the fee is that. And we just have completely different rules. Same idea. In these situations, the function is defined on pieces of the domain and is called a piecewise function. Number 2, the graph below represents a piecewise function. It shows the amount of water in thousands of gallons in a swimming pool after T hours have elapsed. So the bottom axis is time, the vertical axis over there is the gallons, the amount of water sitting in the tank in thousands of gallons. So first question, how has the amount in the pool changed over the domain 0 to 50? That is from time 0 to time 50 hours. How much water was in the tank to start? 2,000 gallons. And then what happened to the amount of water? It increased linearly until we stayed steady up there at 8,000. And then how long were we steady? 10 hours, right? And then it started to decrease until we emptied, right? You can see it's down here on the x-axis. Okay, so that's what the answer to the first question is. I'm not writing any of that. But we're going to fill in this next one together. Over what interval is the water level in the pool increasing? Let's give this a shot. I'm going to write this as an inequality. I know we sometimes use interval notation. We did that last class. I'm going to write inequalities today. From where to where are we increasing? 0 to 20. Agree? 0 to 20. It's that easy. Next question, over what interval is the water level constant? Go ahead and answer that one. Same idea. 20 to 30. 20 less than t less than 30, right? It's constant that whole time. And then finally, over what interval is the water level decreasing? 30 to 50. And 50 is kind of the end of the experiment there. Why? Yeah, great question. What do we do at the endpoints? So here's the deal. Like I said the other day, there's no uniformity among mathematicians for what you decide to do at the endpoints. So some people will say it is increasing at 20. And simultaneously, it is constant at 20. And it seems weird to say both. It is increasing and constant, but it's just a mathematical definition. I'm okay saying both. I'm also okay saying neither. My math lab wants you to say neither. So that's why I'm leaving them off. But it's fine to be confused because the mathematicians are confused. So they're full credit answers, whether you include them or not. Okay, right below the graph, these three intervals, 1, 2, 3, define the different pieces of the domain for our piecewise function. Three different domains, three different pieces of our piecewise function. So here is brand new notation for us. This gobbledygook down here, g of t, we want to make sure we understand exactly what that is representing. So the first thing, 0.3t plus 2. Do you see that? You wrote almost exactly that up above during the preview part. What's the only change? It's not x, it's a t. That's all, right? It's just the variable name is a t. And 0.3t plus 2 is only good for the very first part on the increasing part from 0 up to 20 hours. And so this is how we write that. You say the rule is 0.3t plus 2 if, and you just write the word if, 0 is less than or equal to t is less than or equal to 20. Okay? And then the next piece was the constant piece. And you guys wrote y equals 8, right? That's the constant piece. So the rule is 8, but it's not always 8. It's 8 if 20 is less than t is less than 30. And by the way, this is one of my favorite things about the smartboard. You see what happened there? This little section right in here between the yellow and the green. I mean the yellow and the blue. Can you see it? You kind of do it bigger. Right? Yes, yellow and, yes, it did not do that. Yellow and blue make green. It's just like nature intended it. All right, good. Okay, and then the last rule was the one coming downhill. You wrote up at the top, you wrote negative 0.4x plus 20. We're writing negative 0.4t plus 20, and now we're going to fill in these blanks here. If what? If 30 is less than t, which is less than or equal to 50. That's perfect. Okay, and you should have more endpoint questions, just like Pete asked about the endpoints up above. For sure, we should be confused by these endpoints because now it's like willy-nilly. Some of them are equal and some of them are not. So here's the deal. If you have a circle that is open, like if this very first circle right here were not filled in, but if this were just an open circle, then instead of saying 0 is less than or equal to t, what would it say? 0 is less than t. You guys all know open circle means do not include it. And by virtue of it being filled in, you do include it. The only confusion, therefore, is what do you do when the rules change? Well, this is not the greatest example to think about that because when the rules change, the second rule just picks up right where the first rule left off, and that's not always the case. So as a quick example over here, if the first function had been this, same as it is right there, with an open circle, and then the constant had been up here, then you would say the first rule goes until, I'll put the number, it was 20. First rule goes until 20, including or not including 20. Not including 20. And then the second rule goes from 20 to 30, including or not the 20. Yes, including or not the 30. Including the 30. And then we'll make up one last rule like here. And this one was out at 50, I think. The green rule, including or not the 30. Not including or not the 50. Yes. It's only confusing because these guys all happen to land on each other, right? And so it actually makes no difference which ones you include. You just got to make sure the 20 is in one of those two. Doesn't matter which one you pick. And that the 30 is in one of those two. Doesn't matter which you pick. Okay, and you'll never end up with something like this. What's the problem at 20 there? It's both. Why is that a problem? Why not? Not a function, right? And we're going to be talking almost exclusively about functions for weeks of this course. Not a function right there, right? Okay, on the next page. My cell phone plan with Verizon Wireless charges $79 per month for 700 minutes. And any minutes over this allowance is charged at the rate of, there's a little word missing here, it's $45 per 45 cents per minute, So I'm paying $79 per month fixed, and if I use less than 700 minutes, then I don't pay any more. But as soon as you go over the 700 minutes, you start paying those overage charges, all right? And so it's 45% per minute, starting at the 700th minute. Understand? Okay, we're gonna fill in some blanks here and then make a formula. C of 535. What is the cost of 535 minutes? $79, right? Because you didn't exceed the 700-minute threshold that you paid for. And so we can just write a sentence. It costs $79 for 535 minutes. Okay, the other one is more complicated because the 850 is what? It's higher than the 700. So I feel like I should take that 850 and multiply it by 45 cents. Is that right? No, what should I multiply by 45 cents? Difference, 150 extra, absolutely. So I'll write the formula and then somebody can help us out with the calculation here. So it's 150 times the 0.45. What is that? 67.5. Okay, so is that right? 67.5 is the answer? Still need the 79, right? So it's 79 plus that thing right there, 79 plus. 146.5. Okay. Okay, take a second to write a sentence. The sentence should have exactly the same format as the sentence we've already got. You don't need to talk about the 150. You don't need to talk about the overage. You just need to write a sentence just like the purple one. It costs $146.50 for 850 minutes. So far, so good. Okay. So here's where things get trickier. It's easy to do concrete numbers, but now we're about to build this formula. So coming down here in number 4, C of M. C represents what? The C represents cost, that's our output. M represents number of minutes, that's our input. Okay, so we got two different rules here. On the one hand, I'm actually going to fill in the domains before I fill in the rules. On the one hand, M being trapped between what two numbers is the basic rule. 0 up to 700. What do you think about 0? Include or no? Yes, because if you don't use your phone at all, you're still going to pay for your monthly fee, right? Like Verizon doesn't care if you use 0 minutes, you're still getting charged. The 700, my reading of that is that we include the 700 right here, and that, you know, like we only start to pay once we get past 700. Okay, so then on the other side, so I'll fill in the bottom row here, the domain. What's the first number here? 700. What's the last number up here? Yeah, and Verizon would love for you to be near infinity, right? That'd be awesome. So we don't put anything up there. What about the inequality? Equals or keep it? Keep it. You got to keep it, right? It doesn't, we don't start paying until we get above 700, and that's what that says, above 700. Additionally, it would be very odd for us to have both the 700 appearing in two different places. It can only have one rule. Matt.
You add equals to, well, I think it's underneath or inequality sign.
Yeah.
Restriction. It has to start at 0. You can't go past 700. So that's why it's equal to.
Yeah, it's equal to the 0 and it's equal to the 700 because we're going to have one. It might make more sense once we have the formulas filled in here. Okay, what is the rule if you use between no minutes and 700 minutes? What's your cost? 79, it's easy. It's just always 79. Doesn't matter how many minutes you use, as long as you're up there in that domain. The other one is more complicated. .45 M. I need a little more space here. If 700 less than M.
Minus 700.
So you're saying this? Ivy says that. Jamie says, yeah. What do we think? First choice or second choice? Hmm. Yeah, so you're in that bottom rule if we're more than 700. So the question is it 0.45 M or is it 0.45 times the thing in parentheses? Yeah, like if we do the first one, right? If we did the first one, the 0.45 M, that would say you're paying 45 cents for every minute, including the first 700. And that's not right, right? It's all the extra stuff. And so absolutely, Ivy's got it right. It's this bottom row here. So I'll put it in here, minus 700. And then we'll get rid of that guy. That looks good. Mm-hmm. No, the one we had without that minus 700 was wrong. And I'll show you the example here. Up here in orange, 850 is the number of minutes, right? But we didn't do 850 right here, right? Well, this number just came out of the blue. Where'd that come from? It was 850 minus 700. And we just did it so casually in our head that maybe we lost track of the fact that we did anything at all, right? And so we did 850 minus 700. There it is in general, 850 minus 700, M minus 700. Yeah, so you can see, I mean, it can be tricky, right? Like a lot of people want to just do 0.45 M and that feels right, but you got to exclude the first 700 minutes. Okay, so there's your formula there. And we'll do one last one. We're just going to graph this guy real quick. So here is a brand new piecewise formula, f of x equals, so the top rule is x squared if x is less than 1, and the bottom rule is 1 minus x if x is bigger than or equal to 1. Let's graph these two things here. Okay, so I'm going to just look at this guy right here. So y equals x squared, again, we all know what it is. Draw it in the air with your finger for me. Yep, so we got this little happy parabola, right? And so the only difference between the normal happy parabola, which goes forever left and right, is that this guy has to stop someplace. And it stops at x equals 1. So, so to the left of x equals 1, this parabola is just an ordinary happy thing. I'm not even worried about the scale. Like I didn't pay any attention to which boxes I hit. If you want to be precise, you can plot points over there, right? -3 squared is 9. You could plot that point. What I'm more interested in is being precise when the rules change. So let's think about when the rule changes here. At x equals 1. If x equals 1, are we in the top rule or the bottom rule? If x equals 1, is that the top rule or the bottom rule? It's the bottom rule, because the bottom rule says if x is greater than or equal to 1. So the equals 1 case is definitely the bottom rule. Still, I'm going to plug x equals 1 into the top rule just so that we know where this parabola ends. If you plug x equals 1 into the top rule, you get 1 squared, which is 1. So I'm going to draw an open circle right here at the point 1, 1. And my happy parabola is going to go until that point. How come it was an open circle and not a filled in one? Because it was x is strictly less than 1, not equal to 1. But do you understand that we had to plug 1 in there, even though technically we're not supposed to plug 1 in there? Because otherwise you don't know where the hole is. And you can't say, oh, well, the next number less than 1 is 0. Let's plug in 0. Well, no, there's a lot of numbers between 0 and 1. You didn't get the last one. And there is no last one. Even if you say 0.999, there's still bigger ones. Just plug the 1 in and then exclude it with the hole. Right? So, but it's important to get the location of the hole. Okay, let's play the same game with this bottom one. 1 minus x is a line, right? Uphill or downhill? Downhill line because it's a negative slope. What's the y-intercept of that line? Is 1. And so I'm going to draw something that's going to disappear in a second, but I have a sense that it's going to be here and then like that, right? But why can't I draw just what I did? Yeah, I only get to draw it when x is bigger than or equal to 1. And this stuff over here is no good. So you can't start it at the y-intercept, even though that might be convenient. So what are we going to do? Well, we're going to plug x equals 1 in there. See what we get. When you plug in x equals 1 in the bottom row, 1 minus 1 is 0. So that's the point 1 comma 0, which is right there. 1 comma 0. And this bottom one is a line, so if we just had one more point, that's enough to connect the dots. For example, if x equals 2, what do you get? Negative 1. X is 2, y is negative 1. I can plot that point. Right there is 2, negative 1. And then we can connect the dots. Okay, so here's the moral of the story. When you're going to graph one of these piecewise functions, you definitely want to graph to plot points at the endpoints, at both endpoints for every piece. In this case, there were no more pieces, but if it had been something like this guy right here is between 1 and 5, and then the next rule starts at 5, for sure I would be plugging in both 1 and 5 into that function. It would give me a starting place and an ending place, and then I'm connecting the dots, all right? So plug in both numbers, both endpoints for every piece, every function that you have. Okay, the activities start on the next page. Take your time. There are 4 problems in this activity. All 4 are word problems. So go slowly and check in with each other.